Yeah, so one.
Good morning, thanks for coming. So, last lecture on Tuesday, we did it over Zoom. I particularly like that format because it felt more efficient for me. So I'm thinking of doing the presentation sessions, which are kind of optional and voluntary over Zoom instead of trying to meet in person. How do you guys think about that?
Yes.
And this time slot Tuesday and Thursday 1 p.m. seems particularly bad for me because I get pulled into these some of the departmental meetings. So I'm thinking of trying to have some time slots on Mondays and Wednesdays. So quick poll, can you guys tell me some times that are on which most of you don't have class? Like say for example, how is Monday 1 p.m. or Wednesday 1 p.m.? How many people could attend to Zoom if on a Monday 1 p.m. or Wednesday 1 p.m. time? Okay, so that's good number. Monday 1 p.m., Wednesday 1 p.m. All right. How about say Monday 1 p.m. we'll keep that because at least half of you seem to be okay with it. Say Wednesday 11 a.m. or 10 a.m. something like that. No?
10 a.m. more right me, but I can do 10 a.m.
Okay, so if not, then how about 3 p.m. on Wednesdays? So I see some of the hands that didn't go up previously now go up for Wednesday 3 p.m. So if we say Monday 1 p.m., Wednesday 3 p.m., can you attend at least one of these?
Yes.
All of you. So what I'll try to do is next week we'll try to have a session on actually that's why I asked do we have classes Wednesday, which officially we don't, so I can't ask you to do anything on Wednesday.
Well, if you did a Zoom, I would.
So if we do a session tomorrow at 3 p.m. Technically all of you should be available, but maybe you're traveling or you have other things that you have planned. So maybe let's not do it tomorrow. Next Wednesday 3 p.m. That will be the first time I could meet because next Monday I have something all day, I can't come. So Wednesday 3 p.m. Okay, we'll try to do like a 1 hour session over Zoom where we'll try to focus on RK4 method and do a few examples related to that. Okay, so I'll send out an email. So that's good. All right, so for today, I want to start with the last unit. We are almost there, near the finish line, module 6, probability and statistics, which is not really a topic in the book, in the textbook by Chapra and Canal. So I provided a handout which was posted on Canvas about 20 minutes back. So if you log in now, you can download this handout. And this is a chapter from this book by Figliola and Beasley. It's called Mechanical Measurements. So what I'm planning to do in 3 lectures is to teach probability and statistics for mechanical engineers with a measurement perspective, meaning how do you use statistics when you're doing measurements. Of course, statistics has numerous applications. So you can, if you learn the basic idea, later you can probably adapt yourself as needed, okay? But at least for now, we'll try to think about probabilities. Now, suppose you are trying to do a measurement, okay? Let me ask you a few questions here. So if you have a caliper or some kind of length measurement or voltage measurement, temperature measurement, any kind of measurement, you do that multiple times. You remember doing that in your lab courses or in your projects or whatever. Why do you repeat measurements? Why can't you just take one value of the length and be happy with it? Yes.
It'll skew your results.
Why would it skew your results?
Because if you get something that's like totally out of bounds possibility, it will change everything. If you only have one piece of data versus if you have multiple, less likely chance of missing.
Okay, so let's get some more responses. Yes.
For accuracy.
Okay, I'm going to come back to you. What else?
To reduce the chance of making a mistake.
To reduce the chance of making mistake. I'm going to come back to you. Yes. Did you want to say something?
I was going to say the same thing, error.
To reduce, sorry, you say it.
To reduce error.
To reduce error, okay. We'll need to revisit that too. What other responses come to your mind? Why do you need to repeat your measurements at least a few times in order to get a final reading? You said what you said. Anything else?
I guess you could say to figure out precision of your instruments.
To figure out precision of your instrument. Okay, what else? Yes,
It's easier to take the extra seconds. It's easier to take the extra seconds to measure, pre-measure at the beginning than having to take the results at the end.
so I think you're going by the proverb, measure twice, cut once. Okay, all right. Any other? Yeah,
To account for different system states,
to account for differences in
system states.
system states. Okay. All right, so there's a lot of responses. So I'm going to pick one. What did you say
For accuracy,
for accuracy? Can you tell me what accuracy means?
how close you are, the less error.
Okay, we're going to step back and again ask the question. When you say accuracy, you mean you have a target in mind and then you don't want to go off target. That's what accuracy means. That is, if you are into marksmanship, if you have a target, you are supposed to, let's say, this is your target, the bullseye. If you take a lot of shots and they are near here, you call it accurate. On the money, on the marks.
Starting route to legacy lens routing.
Okay. Now, if you have the same target, okay, and here's your bullseye, and the shots you take. Is this accurate? We'll answer everything. I'll give you two more scenarios. One more scenario is. Is this accurate? And then. This is accurate. So I want to kind of put some meaning into the word. What is accurate? Is this accurate?
Yes.
Just poll, just all of you just tell me yes or no. Is this accurate?
Yes. Yes.
Is this accurate?
No. Yes.
Yes.
No.
Well, no, it's not. So this is not accurate. That's what you're all saying. So this is accurate. You're all saying this is not accurate. We'll come to the word precise. Okay, we'll define it before we use it. Is this accurate?
Yes. Yes.
Who, one of you who says yes, can you tell me why?
It averages the center.
It's about at the center. Okay, so this is also accurate. Is this accurate? This is what you want to say is not accurate. And now just to tell you, or just for completeness, this is accurate because you wanted to go somewhere and you got there. You wanted to go there, but it's not exactly there, it's distributed around there. So this is what we call accurate, but not precise. Precise meaning the tightness of your hits is not good. That's what precise means. So this is not precise. Is this accurate? It's far off from what you want, where you wanted to go, but it is still spot on. It's just it's precise but not accurate, in the sense it's very tight but not where you wanted it to be. Okay, so this is accurate, precise but not accurate. We talked about this. So this is both accurate and precise. And this is neither accurate nor precise. Okay. So when you talk about error, that is when you are trying to, let's say you take a measurement using a vernier and you get values x1, x2, x3, x4, let's say you go up to 10 measurements, okay? When would you say that this set of 10 measurements is actually precise? How would you say it's precise and how would you say it's not precise?
Precise, like if you have a setup error and they fall within that error range. Like let's say where you're aiming, if you have like +1 or
Let me tell you one thing before you continue. When you do a measurement, by definition, you don't know what to expect. A measurement is a fundamental process in which you are trying to understand what the value of that quantity is, which means by definition, you don't know what the value is. So you can't talk about accuracy with just a set of measurements. You should have a target. We don't know what the target is. All we can do is from here, let's say you have 10 values. How do you judge if they are precise or not precise? That's my question.
Isn't this where your standard deviation comes in and what's acceptable in that?
So you can summarize these 10 values as an average and as a standard deviation. And can I assume all of you know what average and standard deviation are? That you have heard of that, or at least you have seen that in many places. So X bar, the average, is simply Xi, I equals 1 to n divided by n, and standard deviation is Xi minus X bar squared summed over I equals 1 to n divided by n minus 1, the whole thing with a square root. If you're not sure, these are the formulas, okay? So if the standard deviation is small, what were you saying?
That means you're gonna be more precise.
So if the standard deviation is small, that means you're going to be precise. Now, you could have a standard deviation that is about 1% of the average. You could have something that's 10% of the average. You could even have something that's 90% of the average. It could even be about the same value as the average. It depends on what your data is. Think about it like this. If I just take this marker, if this white portion alone is my region of interest, and I want to measure the diameter at each section, this looks like a cylinder, but it's actually a slightly tapering cone. Okay, so the diameter is slightly higher here, and the diameter is slightly lower here. So you won't get all same values for even if you take 10 readouts. If to this I also include the blue portion, there is even a narrower neck, and then there is a section which looks like a hexagon. You see it from this side. So if I measure length at 10 randomly selected spots, I can imagine that the standard deviation could be higher. Okay, so if I take any system, you don't have a control on standard deviation. That is dictated by the geometry or the physics or whatever is going on in that system. You can't really have a control on this. So just by judging the standard deviation, just with the standard deviation, you can't say if that system is having a lot of variations or if your measurement is precise or not. You need something else. Let me give you one more example. If you try to go outside and do a polling of how many sick days do students in the university circuit they take, the number of sick days they take will generally be a small number. Why? Because students are usually young and healthy. They don't take a lot of sick days. I mean, unless they are really sick, which is often rare for people in their 20s. You take the same statistic in a retired assisted living home in which people in their 60s and 70s live. You can count how many days in their life they are actually sick. That number will be higher there. So for that group, the standard deviation will be higher, whereas for students, it could be much lower. In either case, what you're doing is a measurement. You are collecting samples, you are recording some quantity, you are computing an average, you are computing a standard deviation. Now, you tell me, just because the seniors have a higher standard deviation in the number of sick days, does that mean that measurement is faulty? You would agree with me that the measurement process is fine, except you are dealing with a system that has more variation. You can think about another example within fluid mechanics. So if you think of a laminar flow, okay, if you just take any particular point, okay, suppose you put a fluid velocity sensor here. Say, for example, how many of you have taken fluids there? Can you name me some ways to measure fluid velocity at a point? Peter,
I forget what the devices are called, but there is a digital device, a digital monitor. A very simple method would be knowing the knowing the diameter of the pipe. You could then calculate the output. If let's say you have.
No, that's what you're talking about is flow rate. I'm talking about velocity at a point. Okay, let's not turn this into a fluids class. I'm just going to say we are going to use what is called as a hot wire anemometer. Okay, what this instrument does is, if you just, it's like a probe, it's like a very fine wire, okay, and that wire is a constant current is, current is passed through the wire to heat it at a certain temperature. And when a fluid is flowing over this wire, the temperature goes down, so the current is modulated in response to the fluid velocity. So the higher the fluid velocity, the higher current you need to hold it at a fixed temperature. And this principle is used to record the fluid velocity through calibration. Okay, let me not go into any more detail. All I want is, if there is time, and this is the velocity at point 1, okay, V1. If you have a very steady flow, the velocity is going to look like this. You can keep acquiring data, it will look like a flat line, and the variation is very minimal. So you can compute a mean. You can compute a mean value, V1 bar, and then you can also have a standard deviation, I'll call it sigma V. And this sigma V for steady flow, for steady laminar flow, let's say sigma V is about 1/100th of a percent of the average velocity. You all know what is turbulent flow, right? Turbulent flow means the flow has a lot of fluctuations in its velocity. So at the same point, if you had a turbulent flow, you could have fluctuations. Okay, so this is for turbulent flow. And in this case, let's say the fluctuations are about 10% of the average. That's a large fluctuation. That is, instead of 100, you could have something as low as 90 or as high as 110. That's the general implication. Just because the standard deviation is high, you can't call the flow measurement in a turbulent flow as to be wrong or imprecise. Whether you make a call about precision or lack of that should not just be based on standard deviation. That's my point. Okay. So there is mean, there is standard deviation, and then we need a measure of what is called as the standard error. And we are going to think about what that standard error is. You repeat measurements so that you can cover the possible variations in your system of interest. And the general notion is, the more number of measurements you do, you get more confidence about your measurement. If you do it 10 times or 100 times or 1,000 times, we generally believe that our reliability increases. So this standard error should scale with n the number of observations. should scale with number of observations. The more observations you make, it gets better. So when we say standard deviation, so okay, let me ask you this question. Should it be completely independent of the standard deviation, or should it be somehow still connected to the standard deviation?
I guess you could say since it shares notation with it, it should be connected in some way.
Should be connected because arguably measuring a low standard deviation is somewhat easier than measuring a high standard deviation. Why? Because you have the same value repeating a lot of times. You don't have to check it 100 times. You just have to check it like 5 times. Steady flow is easier to measure than turbulent flow. Okay, so it still has to be, is still connected or scales with the standard deviation sigma. Okay, so we are now coming back to this picture. When you say something is precise, you want to now have a quantitative measure to use and decide what constitutes precise and what is not precise. Okay, so we have mean, we have standard deviation, okay, and then now we introduce what is called as standard error, which is defined as the t statistic. I mean, I'm going to tell you a lot of terms which we will only see later, so it will be a little bit of accepting what I say at the moment and then clarifying it. Okay, t alpha comma n multiplied by sigma x divided by square root of n. What are these terms? Of course, sigma x is standard deviation, n is number of observations, and t alpha n is called the students, it's just the name, okay, which I hate by the way. Students t statistic evaluated at a certain value of confidence and n. What is certain value of confidence? We'll talk about that before I give you a table for t, okay? For a second, if you see here, t alpha is a constant. It's going to be some number, and t alpha is usually a number that is of the order of magnitude, maybe 2 to 4. Okay, and sigma x is specific to each situation, and n can be chosen by whoever is collecting data, by whoever is collecting data. It could be an experimenter who is setting up an experiment. It could be a statistician or a pollster who is collecting data. It's something that a user can select. With this information, look at this formula and tell me what is an ideal situation to have in terms of the number of observations. That is, if you choose n large enough, what will happen to the standard error?
It approaches zero as it approaches infinity.
It goes to zero as n becomes large. Of course, n can never be infinity because this is a number we are talking about. This is like how many people you are calling to take a poll or something like that. This can't be infinity. And usually this is selected by what kind of criteria? What kind of considerations go into selecting number of observations? You are in your fluids lab. They ask you to do that experiment with the beads, dropping them through a column of shampoo or glycerine, measure the settling time, and then use it to calculate viscosity. This is one of the experiments. You are asked to repeat that trial 5 times. Have you ever wondered why should I do this 5 times? Why not 4 or 3? Why not 6 or 7? Why 5? Not everything has a great theoretical answer. It's as simple as 5 is about the number of times we can do it in reasonable time. You could do it 100 times, except your lab period is only like 2 hours. Okay? But with that 5, you have some sense of expectation for what is the standard deviation in your settling time. That is, your experiment looks like this. Here's a column of fluid, glycerine or shampoo or something, and you drop your spherical object from the top, and you start recording time from here all the way to, say, z equals 0 to z equals L, and you want to count what is T1, what is T2, and measure the settling time as the time taken to fall a height L. The ultimate measurement here is you have a stop clock, you are doing start, stop, you are reading the time from your stop clock. So the measurement here is T1, that is settling time in the first trial, settling time in the second trial, third trial, fourth trial, fifth trial. If you do this experiment, or maybe you've already done this in your course, you would know that these values differ from each other by maybe like a second or 2, usually not more. So you can compute what is their average, what is their standard deviation, and you can see what percent of the average is the standard deviation. So maybe it's like 0.1% of that. So for a given variance or a given standard deviation in your specific system, you choose n such that you make the standard error as small as you want. And choosing n does not happen in vacuum. It has to take into account costs and logistical considerations. If you are a pollster, you are trying to gather opinions about, say, an upcoming election or something. How would you design your study? Think about it. How many people would you call up or poll in order to make a conclusion? Sorry?
I mean, if you're being cynical, you can say what conclusion we want to draw ahead of time.
This is statistic, not politics. See, you can do polling, you will have your agenda, that is politics. This is the science of polling. How will you select how many people to ask or to poll? What, if you are really doing this, what considerations will be running in your head? Should I call 1,000 people? Should I call 10,000 people? Should I interview 100,000 people? How do you make that judgment call?
I mean, it would probably vary based on how many people you had to do the call. If there was just one.
How do you select how many people to call?
As a percentage of the total population?
Yeah, let's say, do you know the population of Tennessee or at least Memphis? I think it's like 400,000, maybe 500. Let's say it's 500,000. Should you interview 50,000, which is 10%? Should you interview 5,000, which is 1%, or 500, which is 0.1%? How do you select that? Yeah.
First, what size of the, like politically, are we speaking? Because if it would be on the full city level as opposed to something minor like a county, that could
Sure.
change.
So suppose an issue that is citywide, something that the entire city is expected to care about. See, okay, I thought somebody will say this. If you are running a polling company or somebody is giving you a task or a budget, First thing is, how much money do you have at your disposal in order to select the number of people to interview? Because it costs money. Statistics or doing this on the field is a lot about budgets, which is what we should care about as Indians, because when you execute projects, your success is largely judged by how well you manage your budgets. Okay, anyway, so this N considerations that are beyond engineering and science go into selecting N. That's my point. Financial considerations. So if you're trying to do this settling time, you have to do this in like 10-15 minutes. You can't do this over 2 hours because your class period is only 2 hours. Okay. Or if you're doing polling, suppose it costs $10 to interview one person and your budget is say some $2,000. That means 200 persons is what you can do. These kind of considerations go into this. That's what I was trying to say. So N can be chosen by whoever is collecting data within constraints. It's not like unconstrained. So if you do all that, what the standard error says is that you can reduce it to as small as you want or as small as possible. All right. What does that standard error mean? Now let me put this question here on a graph. Suppose this is your average. Okay. Suppose the values you collected fall somewhere around here, x3, x4, x5, x6, 7, 8, 9, 10. You can keep on doing this. What is the true value of this quantity? When I talked about my cubic velocity example, suppose x represents the velocity at this point, v1, and each of this is one particular value of the velocity at a given point of time. Which amongst these is the true value? Is there a true value?
You can't tell just by measuring.
You can never tell by measuring, but what you can tell is, suppose you take this x bar, and then you can count or consider an interval plus or minus SE. That is, say, suppose here is x bar, here is the standard error. So this is x bar plus SE, and here is the standard error, x bar minus SE. Suppose there is a mythical truth. There is some real value that there is out there which we can never measure. At least I can ask the question, what is the chance that the true value lies between x minus SE and x plus SE? The question making sense to you? We are not measuring the true value ever. But what we measure is the mean, which is based on a finite number of observations. Where is that for? Sorry. It is based on a finite number of observations. And then we compute standard deviation. And using standard deviation, we compute standard error, which depends on, among other things, inversely on the number of observations. So I am now asking the question, I want to know with what percentage chance does my true value lie between x minus SE and x plus SE? That's one question. Let me write that down.
Would be 100 minus the standard deviation percentage.
Let me write it down and then I'll answer your question. So first question I want answered is, what is the chance that the true value of x lies between x bar minus SE and x bar plus SE? Okay. Second question, standard error scales inversely as number of observations to the square root. So as you said before, as n goes to infinity, standard error goes to 0. What does it mean? What does that mean? What do we say?
that the larger selection you have, the smaller standard error range you will have.
So if you make more observations, you will have a narrower range,
Yes.
right? All of you see that? If you make more observations, your reliability of the mean increases. Okay, in an extreme limit, if you really make n or the number of observations to be really large, this number will be a very, or this range will be very, very narrow. Like for example, suppose this is 1.00 and standard error happens to be 0.001 or 0.0001. So this is like 1.0001 0.9999. So if you care only about 2 decimal points, this is practically 1.00. So how do you increase the reliability of your measurement, of any kind of measurement? By reducing standard error. And to reduce standard error, either your system naturally has less variability, which reflects in the standard deviation, or you make a lot of observations so that you eventually get a small standard error. This concept making sense to you? This is about how do you increase reliability of your mean. So this range here, what is the chance that the true value of x lies between x plus SE and x minus SE? The answer to that is on the t statistic. This alpha here is 1 minus p. That is, if you want to have, let me write it separately here. Suppose to contain the true value of x in the interval x plus SE and x minus SE, p, the probability is chosen typically 95%, so that we can take it as x plus minus SE contains the true value with 95% probability. And this P directly goes into the calculation of T alpha, where T alpha is 1 minus P and N is number of observations. Now that can be a little unsettling because I never told you what T is. I'm just telling you it's a value that you can look up. It is called the student's T parameter, and it is tabulated. We'll see it when we talk about distributions. I'm starting this whole discussion with one simple assumption that you know what is mean standard deviation. You know what probability means, at least in a colloquial sense. Okay, I'm assuming all of that as we talk about this. So if you see the handout, page 137 of the handout. Okay, I'm going to bring it up here. Page 137. So if you go to the handout I posted, whatever I discussed so far is in section 4.2 statistical measurement theory, where here you see X bar is the average of your finite number of observations. Ux is the standard error I talked about, evaluated at p%. So how you should read this equation 4.1 is like this. I'm going to write it out, but before I do that, if you call x bar or x dashed as your true value, okay, the true value lies in this interval with a probability of p%. Okay, so let me write it out. Equation 4.1 must be interpreted as the true value which we'll refer to as x bar lies in the interval, I'm sorry, x prime, not x bar, x prime lies in the interval x prime plus or minus ux, where x bar is the average of n observations or trials and ux is the standard error calculated as ux equal to t alpha comma p, I'm sorry, alpha comma n, alpha equal to 1 minus p comma n multiplied by the standard deviation divided by square root of n. Okay, standard error evaluated at p%. So the true value x bar lies in the interval x bar plus or minus ux with p% probability. Now, if you see the table that I'm going to refer to, which is in page 137, table 4.4. So t values, t of alpha comma n can be referred to from table 4.3, page 137. So please download the handout, turn to page 137 in that handout. So please pause writing for a minute. Look at this. This is table 4.4, the students' key distribution table. What we have on the top here, new T50, T90, T95, T99. Okay. What they are saying is, if you want to know, first of all, look at the T values. They, at a given value of nu, they increase with the percentage. For 99, the value is 63, and it as you go down the table, as the number of the value of nu increases, the value generally decreases. So if you see here, if you go left to right, the value of t increases. If you go top to bottom, the value of t decreases. Now you should know this nu is called degrees of freedom. Degrees of freedom, which is nothing but number of observations minus 1. You tell me intuitively, when does your observation or when does your measurement generally become more reliable? As the number of observations increase, as you make more observations, it becomes reliable. So this t parameter, you can also think about it as a measure of the reliability. Okay. T scales with the probability. If you want a higher value of the probability, t value is higher, and t also scales inversely with the number of degrees of freedom. Okay, so to do measure or to do a calculation of what exactly is your true value. First question, can you ever get the true value? Yes or no? You cannot ever measure the true value because there is no one true value to measure. When you're doing a measurement of the length of this marker, you can measure it at any number of points. There is no one point designated as your target. Okay. So what we can do always is do a finite number of observations, get a mean and standard deviation, and then make this determination about where the true value is likely to be found with a certain probability, and that range where it is likely to be found is x plus or minus the standard error. The standard error is a quantity that depends on three things: the standard deviation, which is inherent to your system. You might be measuring a turbulent flow, you might be measuring something that has a lot of variability or something that has no variability. And what is n? What is that inherent to? Who decides n?
The data set.
The experimenter, or it is really related to the experimental design. What are you saying? But yeah, that goes into experimental design. So if I put the word n, depends on experiment design. I mean, if you are the person carrying out a study, it could be a laboratory study, it could be a field measurement, it could be a polling, it could be any kind of data collection. You take into consideration all such constraints like budget, logistics, availability, number of or available time. So many things go into experiment design. Okay, and this t parameter, the t parameter is a statistical parameter. So it is a statistical parameter that talks about reliability in general, and t scales with the value of t scales with the probability. That is, if you want something to only 50% reliability, it is a smaller value. If you want something to 99% reliability, it is a higher value. See the first row, it goes from 1 to 63. As you go, as the probability goes from 50 to 90 to 95 to 99. Okay, so this is a measure of reliability. Some of you would have taken machine design class. When you do design, you include what is called as safety factor. What is that safety factor? How do you think about it? You have a maximum stress computed in your calculation or your design. You take that number, you multiply it by 5 or 10 or 20, whatever your safety factor is, so that even for the situations that you did not anticipate, your component will still function, because you thought, I estimate say 1 gigapascal, but there is a chance that it could be 40 gigapascal for all I know. So I'll include a design safety factor. T statistic is something like that, which captures the reliability to which we want to know the true value. And then it also scales with number of observations. So if you go from first row to the last row, as you go from 1 to 30 to 60, you can see that the value decreases from 1 to 0.67, or if you see the T95, it decreases from 12.706 all the way to 2.00. So it's a number that becomes smaller with more observations. So to put this together in your head, let's do like a very simple example. All right, problem 4.21. Let's attempt that problem together. Oh no, not that problem. Sorry. Yeah, problem 4.24. Problem 4.24. So a batch of rivets is tested for shear strength. A sample of 31 rivets show a mean strength of 924.2 megapascal with a standard deviation of 18 megapascal. Estimate of the mean shear strength for the batch. I think there's a grammatical mistake here. Estimate the mean shear strength, or estimate the true value of the mean shear strength for the batch at 95% probability. That should be the question. So if you see here, the mean strength is given as 924.2. Your X bar is given to you. Standard deviation of 18 megapascal. So let me write this here. Problem 4.24. X bar is given as 924.2 megapascal and sigma x is given as 18 megapascal. What you are asked to calculate is x dashed, which is the true value, or I should say, we are asked to estimate the range x bar plus minus ux within which the true value x prime is contained with p equal to 95% probability. And ux, the formula for ux is t evaluated at a certain probability multiplied by comma nu, which is number of observations minus 1. So nu is degrees of freedom, which is equal to n minus 1. In this case, this is 31 minus 1. And ux is t alpha comma nu multiplied by sigma x divided by square root of n. This is not about testing your ability to compute an average or a standard deviation. All I am trying to convey is that you can take these numbers, the mean, the standard deviation, and eventually, how do you estimate what is the true value? That is what I'm trying to convey to you. What you measure is not the truth, but how can you say something about the truth based on what you measure? That statement makes sense to you? What you go out in the lab and record as data, that is not directly the truth, but it is telling you a story which you have to uncover with these statistical tools. So you can do this calculation pretty easily. How do you read t value? That's the thing that we want to practice. So go back to page 137. Go back to page 137. Pretty simple to read the table. Wait, it's not 137.
131.
131. Yeah. So t value, our confidence level is 95%. So you have to look in the third column, and our degrees of freedom happens to be 30. So this is our value right here. 30 degrees of freedom, which is 31 minus 1. And then T95 is what we want. So hope you can see this. The value we want is for T is 2.042. So T value is 2.042. 2.042 multiplied by standard deviation is 18 megapascal divided by square root of number of observations is square root of 31. So put this in your calculator and tell me a value of ux which should have unit of megapascal, same as the standard deviation and the x bar.
6.60157.
6.6015 016 megapascal. And since here we have 2 significant figures and 4 significant figures here, we'll just say this is 6.6 megapascal. (6.6 megapascal). This is all easy stuff. I've given you a formula for your exam. You will have access to your textbook. There is no mystery here. The real test is coming after this step, where you have to write one sentence in the end that answers the question. What is that sentence? What is the question, by the way? The question is, we are asked to estimate the range in which we can find the true value. So you have to write that one sentence. Can I erase the top row here? So if you visualize this, here is x bar, 924.2 megapascal. And then you have to take 6.6 units to the right and left. So what is 6.6 to the right? X bar plus ux, which is equal to 930.8. 930.8 megapascal. And then 6.6 units to the left equal to 917.6. 917.6 megapascal. So the important sentence that or important inference here is x bar, the true value of, I'm sorry, x prime, x prime, the true value of x lies between 917.6 megapascal and 930.8 megapascal with 95% confidence or probability. So please write this down, I'll wait. So it lies in a range that spans about 12 megapascal. You have a span of about 12 megapascal between this number and this number, right? You're done writing. Answer this question for me. This statement means your true value could be either 917.6 or 930.8, and all of them, or it's somewhere between there. So it could be either the lowest or highest. You don't have control on that. Number one. Suppose you want to say this with 99% certainty, what would you do?
Just change your T value from the chart.
Update the T value to 2.75, and if you do that, the range will become wider. Right? If you want to be 99% sure, it lies in a wider interval, and you can redo the calculation. And what you would do is, instead of 2.042, I'll write UX for 99% is 2.750 multiplied by 18 megapascal divided by square root of 31. 8.89, thanks. 8.89 megapascals. So if you want to say this with 95% certainty, it's around 6.6. Here it's about 8.9. Okay, so the interval becomes wider. Likewise, if you want to say this only with 50% chance, you just have to multiply with 0.683, and you will see that the interval will actually get narrower. It will get narrower. If you want to say this with 50% chance, it will get wider. If you want to say this with 99% chance. All right, you have done your measurement. You have written an elegant statement saying where the true value of the quantity is likely to be. Now, suppose you are doing this as part of a real engineering design exercise. Suppose this represents a stress value or a velocity value or a temperature value, which is of some consequence. Suppose you are trying to design a heat shield for spacecraft applications or aircraft applications. You are saying my temperature of the tip after all the blocking the insulator does could be in a certain range. Now you have to take real decisions based on your estimate. Do you see that? If this is the range where the true value is likely to fall, you have to use this number as part of a multiple step design process. Do you see that process in your head? You have to understand that neither this nor this is the true value, but it is somewhere in between. Okay. Now every process has some degree of variability, or it requires some degree of reliability. You would agree with me that if you are trying to design a cast iron disc used for cooking versus some kind of a structure that is part of a spacecraft and it's going to re-enter, the question of variability is much higher in the spacecraft than in the kitchen. Mainly because the cast iron, even if it deforms a little bit, grows a little larger because of the heat expansion, the consequence to your cooking is not much. But for a spacecraft, it could be disastrous. Okay, so you choose this the probability value based on how much certainty you want to assure in your design or in your measurement. This number, if your measurement is not of really high stakes, you could choose a lower value. If it's really high stakes, you don't even want to stop at 99, which still gives you 1 in 100 chance. You might want to go for 99.9, or even higher, 99.99 and so on. You just have to calculate more values of t and use that in your calculation here. Okay, that's number one. The other thing is the true value is here in this range. The measurement itself can be improved based on these estimates. Suppose you want to make this interval even narrower, but you don't want to go for a higher confidence level necessary. What else can you do to make your measurement of the mean more reliable? What else can you do in order to say my true value is suppose this is 6.6 megapascal. I want to push this down to 3 megapascal. I want to be able to say something. My true value is 924 plus minus 3 megapascal. That's the tolerance my application can tolerate. How will I accomplish that without going for higher confidence?
Increase number of observations.
I assume you are going to say the same thing. Yeah. You can make this more reliable by making more observations. So as you can see here, as n becomes larger, you can easily shrink this interval. But what is the cost of making more measurements? Monetary, time, logistical, and so on. Okay, so that is where you actually have to be a decision maker. You have to decide. It's so easy to do this in a statistics class. It's just punching numbers, but on the field, n equals 31 and n equals 62 could be the difference between your project actually being successful and getting sunk because of the budget or expensive. So that's where real engineering comes. Okay. All right. So hopefully this gave you an idea of how to do this calculation and then what this interval means. Any question before we do one more example? Yes.
So could the true value, I was a little confused, can the true value be those two range? No, they cannot. Okay.
You can never say x equals 920 is the true value. That statement, it cannot be right. What can be right is x prime is between 919 and 921 with a certain degree of probability, as you can determine by making enough number of observations. That is, think of this range. I'll come back to it. You can take the width of this range. That is how reliable your mean is, how much you can trust it. So if I have a fever, I have a home thermometer, I read 99, and if the error on that, the reliability range on the thermometer is say 2 degrees Fahrenheit, my fever could be 101 or it could be nothing. It's only 97. So that's not a useful measure. What you want in practice is this range to be as narrow as you can make it allowed by your constraints, so that you can actually get some certainty about your mean. So you should never say this statement is blatantly false. That is x bar equal to 920 megapascal with 100% chance. If there is one statement that you should never make, it is to say anything with absolute certainty. This cannot be done, should not be done. What was your question?
I was just gonna ask, so it's a range between those two values, but it doesn't include those two values.
Well, that is, for all practical purposes, you can include these two values. If you want to be really mathematical about this, because in mathematics, if you take any two numbers, there are an infinite number of numbers between them. In engineering or in measurement, it's about the resolution with which you can collect data. So suppose your instrument has a resolution of 0.5, it is meaningless for you to think 917.1 after 917. It has to be 917.5. So don't take this in a literal mathematical sense. Other comments, including I didn't understand what's going on. Today's takeaway is for you to do a finite number of observations, The story doesn't stop with standard deviation. Getting a certain standard deviation doesn't mean anything. It's about how you convert the standard deviation into a standard error and then use that error to understand where your true value could really lie with some chance. That chance could be 95% or 99%. And this interval, which we measure to a certain degree of confidence, it is commonly called confidence interval. Confidence interval. So if I say x bar plus minus ux and put 95% next to it, that is shorthand for saying my true value is likely to be found between x bar and ux and x bar and minus ux with 95% chance. This is like a compact way of saying that. So if you had written down this sentence, below that sentence, just write confidence interval means x bar plus minus ux with 95%, which literally is the shorthand for this sentence.
If our like value for degrees of freedom isn't on there and like lies between two like points on the,
Degrees of freedom is an integer.
but like, do we interpolate?
You can interpolate, and there are actually subroutines in Excel and MATLAB which will allow you to calculate this t value for any value of new and confidence. You don't have to interpolate, you can use that subroutine. The other thing is, if you notice the trend, here, up to say from 1, 2, 3 and so on, the variation is significant. So it goes from 1 to 0.8 to 0.76, 74, 72. But after a while, if you notice here, the change is only in the third decimal point. When it goes to 20, 21, 30, 21 to 30, the jump isn't much at all. And if you see here, 60 and infinity, that's a huge jump. The jump is only 0.005. There is a story to that. This is where the student's t distribution merges with the Gaussian or normal distribution, which is the story of our next lecture. So to your question, if your degrees of freedom is 742, that is practically infinity. In fact, when you're doing measurements in the lab, any observation more than 30 is considered large and anything less than 30 is considered small. So small is sort of like a line we draw at 30. Small sample set, less than 30. Large sample set, more than 30. That's it. Okay. So you don't have to interpolate. That's my point. So let's try just one more example. I'm expecting the TA will be here any moment to distribute the homework. So we did problem 4.24. I want you to try problem 4.25, which is really the same thing. We're just going through one more example. Problem 4.25. Read the problem and let's try it with the table in page 131. 3 independent sets of data are collected from the population of a variable during similar process operating condition. Statistics are found to be N1 equals 16 observations, X1 bar, the mean value is 32, and S of X1 is basically standard deviation of X1 is 3. So 32 is the mean and 3 is the standard deviation. 32 is the mean and 3 is the standard deviation. Okay. So what you want to do, compute an estimate of the pooled mean value of this variable. All right. I'm just going to ask you to try now. Compute the range in which the true mean should lie with 95% confidence.
Just for the first.
Just for the first. We are not going to do pooled set yet, but at least just for the first, compute the range in which the true value should lie with 95% confidence. Here is your incentive for showing up today. You can expect one question on calculation of the true mean or the interval in which the true mean might be contained. That you can expect in your exam. Yes.
So will we not take the SX1 value here?
Yeah, you will. That is the standard deviation. So whatever I use as sigma x, they call it Sx.
No, wouldn't that be? It's like the standard deviation is like the square root of SX squared over n minus 1. Isn't it?
They have already given you that value. No, what? I didn't understand your question.
Like, isn't the standard deviation that value squared over n minus 1? Then you take the square root of that.
I thought Sx is that value.
That is correct. This is showing us that is just the standard deviation with the column.
Now let me just check what their notation is. So if you see here in table 4.7, they have described their notation. Sx is what I wrote as sigma x. So in that problem, if they say 3 units, this term is 3 units. So simple problem. First question is, I know you can do the calculations. You have 16 observations. So what does that mean for your degrees of freedom? 1 less, 15, right? 15. 15 observations or 15 degrees of freedom and 95% confidence. So if you go to page 131 and look up the table, so degrees of freedom is 15, 95% confidence, 2.131. That is the t value. So Sx is 3, t value at 95% probability and nu equals 16 minus 1 is 2.131. Number of observations is 16. So ux is t multiplied by Sx divided by square root of n. 2.131 multiplied by 3 divided by square root of 16, which is 4. So you can find out what this number is.
1.59825.
1.5982, let's say 5983. Okay, so your x bar or your x prime, the true value lies between x bar plus minus ux, which is, what is your x bar? 18? 18? 18 minus 1.59, or I'll just approximate it as 1.60, and 18 plus 1.60. So the statement you have to make is the true value of x lies between 18, what is 18 minus 1.6? That is
X bar is 32.
2.4, X bar 32.
32 observations.
X bar is 32.
Oh, x bar is 30. So x bar is 32. So I have 32 minus 1.60, which is 30.4, and 32 plus 1.60, which is 33.6. So x bar lies between 30.4 and 33.6 with 95% confidence. That is the conclusion you can arrive with the information provided. If you are having a constraint, that is whatever your true value is, you want your true value to be the mean plus minus, say, a delta, where in our case, the spread is 1.6 units. That is, yeah, the spread is 1.6 units. Okay, let's say your target for delta is only 0.1. You want something nailed down to within 0.1 units. What would you do to get there? One obvious thing you can try is, you can't change your system, but at least you can do more measurements. You can collect, instead of 16 samples. So an exam question or a homework question can read like this: how many measurements, how many more measurements are needed to restrict UX to 0.1? With the same standard deviation, assuming, because when you think of a system, you can't do anything about the standard deviation. It is what it is. The only thing that is in your control is the number of observations. Okay. All right, good. I was really hoping the TA would be here, but it's almost class time, end time. So let's stop here, and next Tuesday we'll discuss normal distributions. Okay, and I'll be posting a homework on this topic later this weekend, and we'll continue on Tuesday. Thank you.